So today's class is about a huge scientific breakthrough, and it's about the joining together, the unification of electricity, one force, and magnetism, another force, into kind of a unified, joined together super force that we call electromagnetism. I called it the sunlight, today's class Sunlight Special. Sunlight Special because up until the unification of electricity and magnetism, it wasn't known what sunlight, for example, is. After the unification of electricity and magnetism, we understood what sunlight is. It's bundles of electric and magnetic fields. Anyway, today's class, we're going to talk firstly about how electricity and magnetism got joined together, about the clues that they are joined together, and then literally how they are joined together. And then we're going to talk about the most famous, the classic prediction of joining together electricity and magnetism, which is the prediction of electromagnetic waves, which sunlight, for example, is an example of electromagnetic waves. So we'll discuss the properties of electromagnetic waves that underlie the properties of sunlight, for example. And this is just to remind us that sunlight is important. Sunlight is not just nice. Sunlight is important. Sunlight provides the energy that keeps us alive. It provides the energy that produces the food that we eat and generates the oxygen that we breathe. So understanding sunlight is scientifically interesting. Okay, so the unification of electricity and magnetism is due to James Maxwell. It happened in the 1800s. It's really a second great unification in physics. The prior unification before James Maxwell and electricity and magnetism was the unification by Isaac Newton, in which he unified celestial motion and terrestrial motion, so the motion of the moon with the motion of things on Earth, through Newton's law of gravity. So those are the two greatest unifications of physics over 4 centuries of physics work, basically. The key prediction that came out of the joining together of electricity and magnetism, as I say, is the existence of an electromagnetic wave. So an electromagnetic wave is a bundle of electric and magnetic fields. It's just pure fields, pure EMB fields. And it sustains itself, it propagates itself through a process in which the electric fields are creating magnetic fields, but then the magnetic fields are creating electrical fields. And so it becomes self-sustaining. And that's what electromagnetic waves are. They are self-sustaining bundles of electric and magnetic fields that carry both energy, that's very important. They also carry momentum. That's very important. So they are waves, electricity and magnetism, that are transporting energy and momentum. So one obvious clue, I'll mention one obvious clue to a link between electricity and magnetism, and one less obvious clue to a link between electricity and magnetism. The obvious clue to a link between electricity and magnetism is that electrical forces are forces between electric charges. So at the root, at the core of electrical forces is electrical charge. Electrical forces are interactions between bodies, objects with electrical charge. Magnetic forces are forces between moving electrical charges. So at the root, the core of magnetic forces is also electrical charge. Moving electrical charge is the source of those magnetic forces. So both electricity and magnetism would be absent, would vanish without electrical charge. Both electricity and magnetism are built on, constructed on electrical charge. So that's an obvious link between the two. It's interesting that the electrical field that is produced by electrical charge, here's a sketch of it, is a field that starts on or ends on the charges. The charges are beginnings or ends of field lines. Whereas in the magnetic case, the magnetic field that transmits the magnetic force, well, moving charges or electrical currents are sources of loops of magnetism, loops of magnetic field lines. So although charges are the source of both electric and magnetic fields, how they source, how they create their electrical magnetic fields is different. One's loops and one's beginnings of ends of field lines. The second clue, the less obvious clue, is the clue of induction. So induction was this process in which if we change a magnetic field by one way or another way, I mean, we could change a magnetic field by moving around a bar magnet, or we could change a magnetic field by switching on and off an electrical current. Whatever way you change a magnetic field, increase it, decrease it, switch it on, switch it off, you create a momentary, an instantaneous induced EMF, induced current. That's an electrical effect. The current is driven by the EMF, an electrical effect. So that's too, induction is a link between electricity, the worlds of electricity and magnetism. And that link was the key clue that led James Maxwell to complete a unified theory of electricity and magnetism. So what Maxwell hypothesized was that, there's a B missing here, electric and magnetic fields are able to create each other. So the extra step he took beyond magnetic fields creating induced EMFs, induced currents, was that electric and magnetic fields, when they change in time, can create each other. So his hypothesis was that if you have a changing magnetic field, it creates an electrical field. So changing in time magnetic field creates electrical field. That causes the induced EMF, the induced current in induction. If you have a changing electrical field, so a time-varying electrical field, he hypothesized that would create a changing magnetic field, that will create magnetic influences, magnetic effects. And so he expanded the world, he amplified the world of induction to one in which simply time-varying electric fields, time-varying magnetic fields will create corresponding magnetic and electrical fields. That's pictured here. So in green on the left-hand side here, this is meant to be a picture of a time-varying magnetic field. So maybe this magnetic field is getting stronger with time, more field lines, or maybe it's getting weaker with time, less field lines. And Maxwell hypothesized that that is creating an electrical field, loops of electrical field line that actually create the induced EMF, create the induced current in the circuits. And so this is what we would now call magnetic induction. This is an understanding of Faraday's law of induction. But he also added a new effect that's over here on the right-hand side. In this sketch over here on the right-hand side, we've got a time-varying electrical field. So that's the field lines in orange. they're varying in time. So maybe the field's getting stronger with time. Maybe the field's getting weaker with time. There's getting more field lines or less field lines. And that change in electrical field is creating loops of magnetic field. And that's what we're seeing here in turquoise, or whatever this color is, teal. We're creating loops of magnetic field with this time-varying electrical field. So this is a new phenomenon. This is something completely new. This is not the induced EMFs. This is not an induced currents. This is an explanation of the induced EMFs, the induced currents, but this is a completely new phenomenon that's creating a magnetic field. But you see a nice kind of symmetry or pattern in this hypothesis, right? It's a hypothesis in which both an electric and magnetic field can create the other field, the magnetic or the electrical field. They both create it by varying in time. They both create loops of electric or magnetic fields by varying in time. So there's a lot of symmetry or, built into this, this hypothesis. This slide shows you, it's like a picture book of Maxwell's complete theory of electromagnetism. So we're not going to write down the full equations for Maxwell's complete theory of electromagnetism, but you can write down sketches that represent Maxwell's full theory of electromagnetism. And that's what's on this slide. So take this slide as Maxwell's complete theory of electromagnetism in cartoons. There's 4 of them, okay? And those 4 sketches here correspond to the 4 ways that you can create either an electric field or a magnetic field. So Maxwell's electromagnetic theory, there's 4 different ways, 4 ways you can create electrical magnetic fields. 2 of them you're very, very familiar with from electricity and magnetism. A charge, a point charge, for example, creates a surrounding electrical field. So this is one familiar way that you can create an electrical field with a charge. A moving charge creates a magnetic field. This is a second very familiar way that you can create a field, a magnetic field. So this is electricity, and this is magnetism. These are the separate worlds upstairs here of electricity and of magnetism. And then here's the 2 new ways that you can create electric and magnetic fields. So a time-varying magnetic field, in addition to a charge, creates an electrical field, and a time-varying electrical field, in addition to a moving charge, creates a magnetic field. So those are the 4 ways, 2 new ways, 2 old ways, that you can create electric and magnetic fields. And then the idea is simply that electrical charges experience electromagnetic forces when bathed in these electrical magnetic fields, and that the total electromagnetic force of this sort of grand theory that combines electricity and magnetism is the sum of the electrical force on the charge and the magnetic force on the charge. So this last statement here says how these fields create forces, how the electrical field creates a force, how the magnetic field creates a force, and how that creates a total electromagnetic force. So this is a complete theory of electromagnetism in one slide. So the key prediction, the most important prediction from electromagnetic theory, as I've mentioned, is the existence of a wave of electromagnetism. It's a wave of electric and magnetic fields. It's a bundle of electric magnetic fields that can propagate, can sort of self-propagate, keep itself moving, and can self-sustain, can keep itself waving, basically. And so that's an electromagnetic wave, and importantly, as I've also mentioned, that electromagnetic waves carry with them energy, so that they transport energy from place to place. They carry with them momentum. They transport momentum from place to place. If you wanted to create an electromagnetic wave, what do you have to do? Right, homework. Go home, create an electromagnetic wave. The way you would create an electromagnetic wave in electromagnetic theory is that you would take a charge, for example, and you would say oscillate, vibrate that charge to and fro. So I've got a charge here, and I'm moving it to and fro. I'm creating, as I move this charge to and fro, an electrical field, but importantly, I'm creating a time-varying electrical field. So I move the charge to the left and move the charge to the right. At any location around the charge, the electrical field is changing, is varying as I'm moving the position of the charge. It's changing and varying. So my moving charge is a source of a time-varying electrical field. Well, that creates a time-varying magnetic field. Time-varying electrical fields create magnetic fields. So it's going to create a time-varying magnetic field. But then that magnetic field, that time-varying magnetic field, creates another time-varying electrical field. And so you see that this self-sustains itself. You start with a time-varying electrical field, it creates a magnetic field that it itself is time-varying. That time-varying magnetic field creates another electrical field that is itself time-varying, and so on, and so on, and so on. And an electromagnetic wave just spins out from the oscillating charge, just rolls away from the oscillating charge through empty space, carrying energy, carrying momentum that I'm putting in by moving the charge. You can do exactly the same thing with an electrical current. Supposing you have a circuit with an electrical current, and you change or vibrate or oscillate the electrical current. We change it from going to the left to going to the right, to going to the left, going to the right. That's going to create a surrounding magnetic field. The electrical current's creating a magnetic field. It's going to create a magnetic field that changes with time because the current is changing with time. And so at any location around that current, the magnetic field must be changing with time. Well, that time-varying magnetic field will create an electrical field. And that electrical field itself is time-varying, so it creates a magnetic field. And that magnetic field itself is time-varying, so it's going to create another electrical field, and so on. So a time-varying current will also generate an electromagnetic wave that propagates out, spreads out through space, carries energy and momentum through space that I'm putting in by oscillating the current, by varying the current. And so that's how electromagnetic waves work. The first, so this is Heinrich Hertz, who was that's a hypothesis of Maxwell, right? I mean, maybe it's not true, but it is true. And the person that proved it was true, that joint theory of electricity and magnetism, and that prediction of electromagnetic wave, the person that proved that was Heinrich Hertz. What he did in the lab for the first time was to create artificially an electromagnetic wave and to detect in a detector that electromagnetic wave. So he was the first person to artificially, in the laboratory, make electromagnetic waves and detect electromagnetic waves. And he did it exactly the way I described, by taking either a charge and oscillating it to and fro very quickly with an electrical circuit, or taking a current and oscillating it to and fro very quickly with an electrical circuit, and then creating a wave of electromagnetism, electric and magnetic fields, that was spreading out through the lab and detecting it in another circuit, detecting that electromagnetic wave in another circuit. We're going to take a look at his experiment. We've actually got it here. You'd be pleased to know. So this is the transmitter of the source, we call it the transmitter, of the electromagnetic waves. This is a electrical circuit. I won't go into the details of the electrical circuit, but it does what I mentioned. It charges up these two arms, the one on the right here, the one on the left here. And it charges them oppositely charged, so one to be plus and one to be minus. And then it quickly reverses that to make the other one plus and the original one minus. And then goes back again. So if you could see the charges on this antenna on the left, on the right, and this antenna on the right, supposing, positive charges were red and negative charges were blue, you would see it going red, blue, red, blue, red, blue, as the charges are oscillating on the ears of the antenna. It also corresponds to an oscillating current, as you can imagine. To turn the positive antenna to a negative antenna, you've got to have charge flow. To turn the negative antenna to a positive charge current, positive antenna, you've got to have a charge flow, current flow. And so not only are we oscillating the charges on the two ends, but we're oscillating currents up and down the antennas. And that oscillation of charges, that oscillation of currents is producing time-varying electric and magnetic fields surrounding the transmitter. And those time-varying electric and magnetic fields propagate out as waves, just like ocean waves, just like sound waves, through Maxwell's theory of electromagnetism. The oscillation of the charges on this device it's very fast. So it operates at, I think, 55 megahertz. So every second, the charges change. Every second, the charges change 55 million times. So every second, we'd see 55 million positive charges here, 55 million positive charges appear over here, and correspondingly with the negative charges. Okay, then here's this is Hertz's detector. Right? You can see, firstly, it's not connected to the transmitter. This receiver, we call it, this detector is not connected to it. It's just a long copper rod, which is going to be bathed in the electric and magnetic fields. It's going to experience the electrical magnetic fields. The electrical fields are going to induce currents. They're going to induce EMFs. And the induced currents and the induced EMFs are going to light the lamps, the little lamps here, the little incandescent lamps on this receiver. So let's see if we can do this. I'm going to... Last class, I opened the bar at the back, but this class I can't. Oh, that hurt. Okay, so here, the circuit is running now. And look, if I bring the receiver up to the circuit, you see the lights being lit. It's detecting the electromagnetic waves. There's no wires connecting these things. They're just completely separate. There's just empty space between them. And so it's electromagnetic waves that are propagating from the transmitter to the receiver is how this communication is occurring. Now, it's a little different from induction. Remember, induction was occurring just at moments, instantaneous moments, that we switched on and off a circuit, for example. Here we've got continuous electromagnetic waves propagating outwards from the transmitter to the receiver, carrying energy and momentum from the transmitter to the receiver. It's costing energy to light these lamps. And that energy that's lighting the lamps is coming from the transmitter, just like energy is coming from the sun to Earth to light us. And so you can see that if I pull the receiver further away, the waves are getting weaker, just like, throw a stone in a pond, right? You get big ripples where the stone went in, and then they move away and they die out. And so exactly the same for electromagnetic waves. The source, if we get close to the source, look at those lamps in the middle now, and as I pull away, It gets weaker and weaker. Still lit. I can still see it. I don't know if you can. But there's one in the middle, right? That's still lit out here. But this electromagnetic wave is spreading out. It gets out to you. It's just I can't detect it with this detector. Okay, so that's Heinrich Hertz's experiment, laboratory experiment, and that was the proof, basically, of electromagnetic theory, that you can produce electromagnetic waves and you can detect electromagnetic waves. I know this is going to get extremely annoying if it goes on. This just shows you a sketch of how it was working. So here's the circuit that charges up the two antennas. At this moment, in red, right, we've got positive charges on this antenna, negative charges on this antenna. But this changes it at 85, not 88. I said 88, but it's 85 megahertz. These are oscillating to and fro at 85 megahertz. They're creating surrounding magnetic fields due to the currents, surrounding electrical fields due to the charges, and they're varying electric and magnetic fields, and they create the electromagnetic waves that propagate outwards, flow outwards, and carry energy and momentum. So that's what's going on here. Okay, so now we've predicted and actually detected, observed electromagnetic waves. That's a massive breakthrough, and we did it in the first half of the class. Quite astounding, I think. We're going to look at some of the properties, the characteristics of electromagnetic waves, because now suddenly we've got a new window on sunlight. We know what sunlight is. It's electromagnetic waves, bundles of electricity and magnetism. In an electromagnetic wave, so say propagating from the sun to the earth, as I say, there's an electric field and there's a magnetic field. And the electric field and the magnetic field and the direction of propagation are related in very interesting ways. So the electromagnetic waves have key relationships between the electric field, the magnetic field, the E and the B, and the motion, the direction of motion. The direction of the speed of electromagnetic wave, for some reason we give it the symbol C. And so on this slide it's denoted C. So the direction of propagation is the C, the electric field is the E, and the magnetic field is the B on this slide. Now the interesting thing for sunlight coming from the sun to the earth, or for these radio waves coming from the transmitter to the antenna, the electric field and the magnetic field and the direction of the wave are all mutually perpendicular to one another. They all seem to love to be perpendicular to one another. What that means is, so this is a model of obviously it's a model of it. No, this is a model of electromagnetic wave. Here, this red arrow, this is the direction of propagation of the wave. So here it is propagating from the left of the room to the right of the room. The electric and magnetic fields in that wave are they're vibrating, they're oscillating bundles of electric and magnetic fields, and they're vibrating, oscillating perpendicular to the direction of motion. So look, this electric field that you can see now, that's up and down, that's perpendicular to the direction of motion. The B field, you can see it now, right? That's perpendicular to the direction of motion. So that's a characteristic of electromagnetic waves. Also, the electric and magnetic fields themselves are perpendicular to each other. So right now, the B field is oscillating up and down, and the E field is oscillating horizontally. So everybody's perpendicular to everybody else. C, E, and B. C is perpendicular to E and B, E is perpendicular to C and B is perpendicular to C and E. It's a world of perpendicularity, which isn't a word. Okay. So that's an interesting thing about the directions of electromagnetic waves, and that actually comes out of electromagnetic theory. It comes out of Maxwell's theory. So it is a prediction of Maxwell's theory. There's another interesting point. As this electromagnetic wave here propagates from the left of the room to the right of the room with its oscillating electric and magnetic fields that are perpendicular to one another, there's a relationship, it's not really shown here, between the amplitude of the electric field, which you're seeing right now, and the amplitude of the magnetic field. You can't have any combination of amplitudes of electric and magnetic fields. There's only a certain combination of electric and magnetic field amplitudes. There's a particular relationship between the electric and magnetic field amplitudes, and it's on this slide here. The ratio of the electrical field's size or magnitude, that's in newtons per coulomb, to the magnetic field's size, which is, of magnitude, which is in Teslas, that ratio, E over B, is equal to the speed that the wave travels at, the speed of light, the speed of an electromagnetic wave. So that's a relationship. E over B equals C is a characteristic relationship between the E and B fields and the speed. That's, again, a prediction of electromagnetic theory, of Maxwell's theory. So not only did his theory predict a relationship between the directions of E, B, and C, but it predicted a relationship between the magnitudes of the E, B, and C. Has this characteristic relationship. This is one of the most amazing equations in physics. It's a very simple equation. Said that, everybody's eyes are glazed over. Why is it the most amazing equation in physics? Well, look, it involves three worlds. Three worlds that were different worlds. Three worlds that are different worlds until James Maxwell. So it involves electricity. The epsilon naught is the electric permittivity, characterizes the strength of electricity. Mu naught, that's the magnetic permeability. That characterizes the strength of magnetism, the intrinsic strength of the magnetic force. And then it involves C, that's the speed of light. That was known at the time of Maxwell. So that's 3 times 10 to the 8 meters per second. Light travels very, very, very fast. Up until Maxwell, those were just 3 different numbers of 3 different worlds of electricity and magnetism and light. Out of Maxwell's theory came a relationship between those. Since Maxwell's theory joined together electricity and magnetism and predicted light, it joined together epsilon naught and mu naught, the electric permittivity, the magnetic permeability, with the speed of light. And this is a key prediction of Maxwell's theory, that the speed of light is related to the intrinsic strengths of electricity and magnetism by this little equation here. The speed of light is just the inverse of the square root of the product of epsilon naught and mu naught. And that comes out, if you try that at home, right, you're probably keen to do that tonight, multiply mu naught and epsilon naught, take the square root of that, take the inverse of that, you'll find you get the speed of light. It's true. Now, that's mildly fun to do, I guess, but imagine what that was like for James Maxwell. So at at the moment he came up, or hypothesized electromagnetic theory, epsilon naught was known, mu naught was known, so those constants of electricity and magnetism were known. The speed of light was known. Suddenly he's got a prediction that if you take the product of epsilon naught and mu naught and take the square root and take the inverse, that's going to be the speed of light. Suddenly that was another theoretical proof of his theory. So that must have been, it's like a good day at the office, right? Good day at the office. Oh, I'll multiply mu naught and epsilon naught, take the square root and take the inverse. Oh, I got the speed of light, right? You know you've discovered something really, really important when that comes out of your theory. So this is a very, very famous equation. I'm not the only physicist that will say that this is one of my favorite equations. So it really is a favorite. Okay. Enough crazy talk. As I mentioned, electromagnetic waves carry with them energy and momentum, just like particles. We're familiar with 211. Remember the joy of 211? In 211, objects, bodies, particles carry energy and momentum. We got very used to the kinetic energy of a particle, the linear momentum of a particle or an object or a body. We're less used to waves, say water waves or sound waves or light waves carrying energy and momentum. So when we think of energy and momentum for particles or objects or bodies, we tend to be thinking of a single object, a single body with that contains a certain amount of energy. Kinetic energy, contains a certain amount of momentum, linear momentum. When we think about waves, whether they're sound waves or water waves or light waves that are carrying energy and momentum, we don't have little discrete amounts, packets of water waves or sound waves or light waves. Rather, we have a flow of water waves, sound waves, or light waves. So we tend to think more about the energy flow that's carried by a water wave or a sound wave or a light wave. And we tend to think about the momentum flow that's carried by waves, like water waves or light waves. The way we think about it specifically is we tend to think about a surface. So here in light blue is some surface. I call this area A. We think about some time interval. So here's a clock measuring the time interval. And we think about how much energy, how much momentum was carried across that surface in that time interval by that wave, whether it's a water wave or a sound wave or a light wave. So when we talk about energy, momentum that's carried by waves, we'll be talking in terms of quantities that represent the amount of energy that's carried, the amount of momentum that's carried per unit surface area per second, so per unit of area per unit of time, as a way of quantifying the energy momentum that's carried by the wave. So I'm going to give you a few equations now I think on this slide and the next slide that relate to the energy that's carried by an electromagnetic wave and the momentum that's carried by an electromagnetic wave. Now, you know that electromagnetic waves carry energy. You just know that. You've only got to go outside on a bright sunny day, right? And you can feel, you can experience that energy. You're warmed by the sunlight. So you know that electromagnetic waves like sunlight do carry energy. We characterize that energy by a quantity called the intensity. That's the I here. It's the number of joules per second per square meter carried by that electromagnetic wave. So again, I'm imagining a surface, I'm imagining a time interval, and I'm imagining the joules of energy that are carried through that surface per unit area, per unit time. That's what intensity is. That's how we describe energy flow, the energy carried by waves. So it's in terms of intensity. And it's, as I say, the units are watts per square meter, or this is really joules per second per square meter, because it's per unit area, per unit of time. These are two equations in which the intensity is written in terms of the electrical field or the magnetic field. So EM here is the maximum electrical field in the electromagnetic wave. BM here is the maximum magnetic field in the electromagnetic wave. So look, by maximum, I mean the amplitude of the electromagnetic wave. So here's the maximum of the electrical field, and here's the maximum of the magnetic field. Here's another maximum of the electrical field. Here's another maximum of the magnetic field. So that's what the EMs and the BMs are. Well, look, it wouldn't be surprising that a stronger electric field, stronger magnetic field would correspond to larger intensities, larger energy flow. But the intensity actually goes as the square of the electrical field, the square of the magnetic field. So the intensity I is in proportion to EM squared. The intensity I is proportional to BM squared. And then the other items in these equations are just these constants associated with electromagnetic theory. So there's a mu naught and a C. You could write these constants in terms of any two of that triplet. Remember, we've got a triplet of epsilon naught, mu naught, and C. So you can write this equation here in lots of different ways involving any pair of that triplet of constants. Here it's written in terms of mu naught and C, which is most often what you'll see. So it means that if you were to double the electric fields in an electromagnetic wave, which would mean that you'd also be doubling the magnetic fields in an electromagnetic wave, because they're tied together, they're roped together, you'd actually be quadrupling the energy that's carried by the electromagnetic wave. You'd be quadrupling the intensity. So this is energy carried, this slide. This slide, so any sunbather knows that electromagnetic waves, sunlight carries energy. Sunbathers generally don't know that electromagnetic waves also carry momentum and exert forces. So if you go and stand out in the sunlight, right, not only is that sunlight that's bathing you transferring energy from the sun to you, but it's also transferring momentum to you. It's exerting a force on you. I mean, you're not knocked over, but it is transferring a momentum to you by exerting a force on you. That force, interestingly, that force was not measured until 1903. There were two famous experiments, one in the US and one in Russia, that first measured the fact that if light is shining on you, it does exert a force on you. It's because the force that light is shining, I mean, I can see the projector right here. It's shining light on me, but I'm not tipping over backwards. It's a very, very, very tiny force that light is directing on me. But we have a demonstration of it. I'm going to put the camera on. So this glass sphere here is evacuated. There's no air in this glass sphere here, so it's completely empty space. Inside the glass sphere is what looks like a weather vane, right? It's got these 4 paddles to it, and what we're going to do is shine light on this weather vane. And because it's in a vacuum, because these paddles are very light, and because they're supported with almost no friction, the force of the light is actually going to turn these paddles. And so this is how the first experiment is done. So it's a bit like, on the top of a steeple, right? You might see a weather vane, and, when the wind blows, it'll turn it. Well, our wind that's going to turn this weather vane is light. There's no wind inside this glass sphere because there's no air inside the glass sphere. It's pure vacuum. Rather, we're going to direct light onto the weather vane and turn the weather vane. So here's the light. It's actually a pretty bright light because, again, this is a tiny force that we're going to try and measure. The force of light is a really tiny force, and so we need something that's very, very, very easy to turn and something that's very bright. So let's try this. And off we go. Right? There's no wind puffing around in there. I think it's an amazing demonstration. It's literally the light is kicking that thing around. And if I turn the light off, it stops rotating. And so that is, that literally is, you've seen the force of light. This slide has, like we had an equation for the intensity of light, which represents the energy that light is carrying in terms of the electric and magnetic fields. This slide is an equation for a quantity that's called the pressure, the radiation pressure of light. But you know that pressure is force per unit area. So it's just the way that we represent forces with waves, for example, electromagnetic waves, is again we represent the force in terms of the force per unit area per unit time, and so that's what the pressure is. So the pressure that's exerted, which is newtons per square meter, by light impinging on a surface is given by either this formula or this formula here. These two formulas are two extremes of two cases. So one case would be where light shines on something and is completely absorbed by something. The other case is where light shines on something and is 100% reflected by that something. So I've got a picture here. Here's what we call total absorption. This is the light coming in, or the electromagnetic waves coming in, and they're just absorbed by it. It's like a brick wall that just stands there and takes that light and absorbs it. And then this is the case of reflection. This is like a silvered brick wall, the light shining on the silvered brick wall, and like tennis balls coming at the silvered brick wall, they just bounce back off it. So in the case of, this is total reflection, 100% reflection. This case actually corresponds to a higher force of light, a higher radiation pressure. This one, a lower force of light, a lower radiation pressure. And it's just like, supposing I threw a blob of clay at a wall, versus a tennis ball at a war, supposing they had the same masses and the same speeds for the clay and the tennis ball, if the tennis ball bounces back, the change in momentum is twice as big. The force is twice as big. If the blob of clay just sticks to the wall, the change in momentum is only half as big. The force is half as big. And that's the same here with the light. So this light is like the tennis balls bouncing off when you've got reflection. This is like the blobs of clay just sticking to the wall when you don't have reflection. They're absorbed. And that's the factor of 2. This is 2 times bigger. This is 2 times smaller. Look, any reasonable material is going to be somewhere in between those kind of extremes. Nothing's actually 100% reflecting. Nothing's actually 100% absorbing. So they're kind of the extreme limits. They're useful approximations. But anyway, this formula tells you that the newtons per square meter, the pressure due to the light, the force due to the light, is in proportion to the intensity. It's just the intensity divided by the speed of the light ray, or twice the intensity divided by the speed of the light ray. So this is a very simple relationship between the energy conveyed by the light and the force that's being exerted by the light. And of course, we already know that the intensity is related to the squares of the electric and magnetic fields. So of course, the forces are also related to the squares of the electric and magnetic fields. Am I going the wrong way? No. Okay, one last comment on the properties of light waves. So what we've done so far is talked about the directions and the magnitudes of the electric and magnetic fields in the light waves. That's a key prediction of Maxwell's theory. We've talked about the fact that light waves carry energy, they carry momentum. We've given equations for the energy and momentum flow in electromagnetic waves. That's a key prediction of electromagnetic theory. The last thing I wanted to mention was the fact that there's a massive spectrum of electromagnetic waves. There's an enormous range of electromagnetic waves, and we'll see that. The distance in space between the peak of this peak of the electric field and the next peak of the electrical field, so this distance in space is what we call the wavelength. It's what we call the wavelength of an electromagnetic wave, but it would be what we call the wavelength of a water wave or a sound wave too. The time between the peak at a given location, the peak of the electrical field, and the next peak of the electrical field. So that time interval, that duration between successive peaks of the electrical field, that's what we call the frequency of the electromagnetic wave. So every electromagnetic wave, whether it's visible light or radio waves that we met here, or some other electromagnetic wave, is characterized by some wavelength, which is the distance interval between peaks of the electric and magnetic fields, and characterized by a frequency, which is the time interval, duration, between peaks of the electric or magnetic fields. And we give those quantities the symbols lambda as the wavelength is measured in meters, f, that's the frequency. It's measured in inverse seconds. It's the number of frequency is the number of oscillations per second. Those two quantities are related to the speed of the wave. And if you look at this equation here, you can see it makes dimensional sense, right? The wavelength is measured in meters. The frequency, that's the inverse of the time interval between two peaks, that's measured in inverse seconds. If you multiply the two together, you get meters per second. That is the speed of the wave. So when we think about electromagnetic waves, we think about them being characterized by a wavelength. We think about them characterized by a frequency. The wavelength and the frequency are tied together because their product equals the speed of light. So if you were to increase the wavelength, make the wavelength longer, you've got to correspondingly change the frequency. You've got to make it smaller. If you were to reduce the wavelength, make it much smaller, then you've got to correspondingly increase the frequency because the product of lambda and f is always going to be the speed of light. So these two things are related. As I mentioned, that electromagnetic waves are actually an enormous spectrum of electromagnetic waves at different wavelengths and different frequencies. And here is a picture of this vast spectrum. So if you look on the left-hand side, this is frequency. And this is frequency from 1,000 hertz, so that's 1,000 oscillations per second, to 10 to the 22 hertz, 10 to the 22 oscillations per second. And we know of electromagnetic waves, we measure electromagnetic waves with that huge range of frequencies. You know, that's a range of 10 to the 20. The wavelengths correspondingly, a huge range of wavelengths. Down here we got wavelengths that are hundreds of kilometers, so enormously long waves. Upstairs here we've got wavelengths that are tiny, tiny, tiny fractions of a meter. This is 10 to the minus 9 a meter. This is 10 to the minus 12 of a meter. There's a thing called a femtometer. That's 10 to the minus 15 of a meter. We know all those electromagnetic waves. So it's a 10 to the power 20 spectrum of electromagnetic waves. This is massive. I can't think of anything that's more massive than that we kind of measure the full breadth and width of. Right in the middle of this plot is a very narrow slither, right? And it really, if it was drawn to scale, you wouldn't even see it. It would be just this finest line. That's visible light. You know, we kind of walk around thinking, well, look, visible light is pretty much everything. I'm seeing everything. You're seeing this tiny, 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 tiny slither of the electromagnetic radiation that's all around us. It's just a little bit from 400 nanometers wavelength to 700 nanometers wavelength that we actually see as from red to violet. Beyond that tiny, it's like looking through some very thin letterbox, right? And thinking that's the whole world. No, that's not the whole world. Beyond, higher than 700 nanometers, longer than 700 nanometers wavelength, and shorter than 400 nanometers wavelength, is a huge amount of electromagnetic radiation, and we're completely ignorant of what's going on there. So most things we don't see. We think of most things we see, but actually almost everything we don't see. Okay. At much longer wavelengths, much lower frequencies are the man-made electromagnetic waves made by this machine. So the 85 megahertz is somewhere way down here. And upstairs here are things like X-rays and gamma rays that are used, for example, in medical fields, right? You use X-rays and gamma rays for imaging. And so that's, those wavelengths are much shorter than visible light. Those frequencies are much higher than visible light. And so this is this kind of full rainbow. That rainbow you see in the sky is just a very thin slither of the full electromagnetic rainbow. We've got a question. Okay, so in this question, it says somehow, you've doubled the maximum the electric field, EM, in a electromagnetic wave, say in a light wave. Does the magnetic field double? Does the speed double? Does the intensity double? So you've got to pick one of those. I'm going to go fairly fast here because I've got a few problems. I want to get to the problems just in case they were on the test. Okay, I think I'll get moving again to the extent that I can. What doubles when you double the electric field? One thing that doesn't double is the speed, right? Light or other electromagnetic waves travel at 3 × 10⁸ meters per second through empty space. It doesn't matter whether it's a bright light or a weak light, intense or not very intense. They're all traveling at the same speed, so speed doesn't change. When you double the electrical field, you double its partner, the magnetic field. So, electric and magnetic fields truly are partners. If you double one of them, you'll double the other one. Their ratio is determined by the speed of light, which is a constant. So doubling E doubles B. If you double E or you double B, you actually quadruple, we mentioned this, you quadruple the intensity. So you quadruple the energy flow in an electromagnetic wave. So the magnetic field got doubled when we doubled the electric field. Okay, so I've got a few questions here. This one I think I'll just talk about on the overhead rather than write it out. The question is about sunlight. So the intensity we talked about intensity, we talked about the force of light, we talked about the electric and magnetic fields in the light. The intensity of sunlight striking the Earth's atmosphere is about 1 kilowatt per square meter. So imagine a square meter, sort of this size. Every square meter of the upper atmosphere is getting, it's 1.4 kilowatts from the sun, 1.4 kilowatts per square meter. And this question is just, maybe a scientifically interesting one. What is the electric and magnetic fields in that light, of that sunlight of that intensity? Well, all I got to do is use those relationships between the electric field and the intensity or the magnetic field in the intensity. We met these two equations. I rewrote them here. So if you know the electrical field, maximum, you can figure out the intensity. If you know the magnetic field is maximum, you can figure out the intensity. Or vice versa, if you know the intensity, which is what we know in this case, it's a 1.4 kilowatts per square meter, we can figure out the electric and magnetic fields. We just got to multiply through or divide through by various constants, the c's and the mu naughts and the factors of 2. And then we just got to take the square root to get the electric and magnetic fields. And if you plug in the numbers here for the intensity, 1.4 kilowatts, per square meter. Plug it in for the equation for the electrical field. Plug it in for the equation for the magnetic field. Multiply by the mu naughts, the magnetic permeabilities. Multiply or divide by the speed of light. So that's the difference between this pair of equations. You get the electrical field and the magnetic field. You see that in our kind of familiar units for the electrical field. Volts per meter, that's the same as newtons per coulomb. The electrical field is quite a large number. It's about, 1,000 volts per meter. On the other hand, the magnetic field, in the familiar units for the magnetic field, that was Tesla's. The magnetic field is a tiny, tiny number. It's order 10 to the minus 6. That's a reflection that E over B, E divided by B, the ratio of E to B, is the speed of light. So we could have calculated the magnetic field from the electrical field by just dividing this number by the speed of light. Or we could have calculated the electrical field from the magnetic field by just multiplying by the speed of light. So, I didn't need to use both of these equations. Actually, once I got one field, I could have calculated the other field in a simpler way just by dividing the electrical field by C to get B, or by multiplying the magnetic field by C to get E. Yeah. Okay, that was fun. Oh, I didn't give you a chance to see that question, did I? That's because I'm getting extremely anxious about getting through this in time. So I'm not even going to tell you what the question is. I'm just going to solve some random problem. We're imagining we've got a 40-watt light bulb. By a 40-watt light bulb, I mean that it's radiating energy at 40 joules per second as light, as, say, visible light. We're going to imagine that we stand 1 meter from that 40-watt light bulb, radiating 40 joules per second, and we're going to figure out the intensity of the light at that distance, and we're going to figure out the electrical field in the light at that distance. So we're going to figure out those two things. Look, the power that the light bulb is emitting, that's fixed at 40 watts. So every second it emits 40 joules of energy as a light. This second, next second, 40 joules, 40 joules, 40 joules. At a certain distance, right, the intensity is going to be determined by that 40 watts. But the greater the distance you are, the lower the intensity. If you're really close to the light bulb, right, that 40 watts is spread out over a small region. If you're very far from the light bulb, that 40 watts gets spread out over a very large region. So whilst the power emitted by the light bulb is constant, the intensity depends on how close or far you are from the light bulb. And so the electrical magnetic fields will depend on how far or close you are. So let's figure out the intensity and then the electrical field at 1 meter. Okay, so here I am. I, of course, drew a sketch. Here's the 40-watt light bulb. That's the power. And what I've drawn here is this is an imaginary spherical surface. This is just going to help me. This is just a helper. It's going to help me because that power is passing through that 1 meter radius spherical shell. 40 watts is passing through that. And the intensity is the power per square meter through that surface. So we want the intensity, that's watts per square meter through this spherical surface. To get the intensity, all I've got to actually do is take the power that is traveling through the entire surface, so I'm calling that P, that's the power of 40 watts, and dividing it, sorry about this, A, that's the area of the surface. So A is 4 pi r squared, which for a 1 meter radius surface is simply going to be 4 pi, and 4 pi is 12.6. So all I've actually got to do to calculate the intensity out here, 1 meter from the lamp, is divide the power that the lamp is producing by the area of this imaginary helper spherical surface. Oh, sorry. 40 watts, 12.6 meters squared, and that calculation came out to be 3.2. 3.2 watts per square meter. And so that's the intensity, 1 meter from the lamp. If we were closer, it's getting really bad, sorry. If we were closer, then the intensity would be greater. If we were further away, then the intensity would be lower. Because the area of an imaginary sphere would be smaller if we were closer, and it would be larger if we're further away. We also want the electrical field, the maximum electrical field. We met this equation on the last slide. The relationship between the electrical field and the intensity, I'll just write it down again, it's the square root of 2 times the magnetic permeability times the speed of light times the intensity. So the electrical field is in proportion to the square root of the intensity. If you plug in all those numbers, what we get is, I won't write them all out, I got 49 volts per meter as the electrical field. So it's this was only a 40-watt light bulb. Remember, the sun's rays were 1.4 kilowatts. This is only about 50 volts per meter. If you remember, the sun's rays were 1,000 volts per meter. So lower power for the light bulb and lower electrical field for the light bulb.